company that's trying to develop a lot of electronic planes and aviation methods. So I'm going to throw it to him, and he's going to give you a presentation about what he does with bioaerospace.
Hey guys, glad to be here. I'm a UCF grad. I actually enrolled last semester to do my Master's of Thermofluid Aerodynamic Systems Design. So I guess I'm a student again from afar. And wanted to go over with you guys a little bit about what I do, but also kind of how I got started. And I really think as if you're particularly interested in aerodynamics and wind tunnel testing, or what we can do with CFD now, I want to share some insight with how that's helped me after graduation. So like Emma said, we are working on an all-electric aircraft. I just minutes ago just got off of our CDR review, which is our critical design review. So we had all of our DERs and upper management listening to us basically justify our designs that we've done for the past 2 years. And the plane right here is what we're building. I work under the umbrella of the composite structures department, and so everything here is made out of carbon fiber. In a small company, we wear many hats, so I actually also have designed this door, designed a lot of the wing ribs, but a lot of my impact comes from CFD and discovering things about the aircraft that we might not have caught until after it was already in production. And those mistakes would have been a lot more costly to the program in terms of trying to get certified under the FAA. So that's our goal. The FAA has told us time and time again that we're number one in the, as far as application scenario, that it's basically our game to lose. If we succeed, we will be the first company to get an all-electric aircraft FAA certified. And if you know anything about FAA certification or the requirements and the safety standards that are involved, it's incredibly rigorous. So it's not just building a kit plane. You know, we have all seen electric aircraft fly before, but to get it to these standards out for market and for purchase and for student pilots to train in is a much more daunting task. Before I get started with CFD, I'm actually going to do an old presentation of something that I shared with my company. Now, none of them were aerospace engineers. A lot of them are mechanical, electrical, composite engineers and things like that. So a lot of you guys might know some of what I'm already going to talk about, but and if there's any questions in the meantime, please let me know. But the one thing that I noticed, and I've had Dr. Osbey, I don't know if he's still there, but he made us do a couple CFD projects with the ANSYS student version. And at the time, I didn't really know. I mean, it was one of those things where it's like, okay, gosh, on top of 4 other classes and graduation's coming up, I got to get this assignment in. So I didn't really retain a lot of, I guess, the information that I wish I would have when it came to CFD. Because if you really want to work in aerodynamics, aerospace, incompressible, compressible studies, things like that, this is the tool, and this is the one thing that will make you super valuable to your future company that you work for. They didn't really, but aside from that one project, I didn't really get exposed to it as an undergrad. And I wish I did now. And, and when I actually got hired on at this company, I was a mechanical designer. It was more of like I was on my way across the country and I decided I loved Denver, Colorado, and said, well, what aerospace companies are out here? Because I don't really want to move. And it was more of like an impulse decision to hire on with the company. and I hired on as a mechanical designer, which isn't even an engineering title in terms of design and applying what we have learned to designs and things like that. It's more GD&T and drawings and things like that, which there's nothing wrong with that. But I noticed this lapse in the company that we're an aircraft company, but nobody's doing aerodynamic analysis. And we were outsourcing a company in California and paying them hundreds and hundreds of thousands of dollars to do this CFD work for us. So I ended up actually teaching myself post-graduation while I was working for this company and behind the scenes putting in a lot of extra hours. And I eventually delivered a package to the chief engineer, the director of engineering, and they said, why the heck is this guy doing drawings? You know what I mean? Like we're an aircraft company. We can do this in-house, obviously, now. So the only reason I say that is because while you're still in school and I know for a fact that you guys get the full-blown ANSYS version as being a student to you. That's going to give you unlimited amount of cells, and I'll explain that here shortly, what all that means. And you can do full aircraft, full rockets. Even if it's your project, your senior design project, you can do full-blown analysis on it that sometimes the student version gives you limitations on. And doing so, again, I go back to if this is what you're interested in, and I think you all are, because we wouldn't be here if we weren't, otherwise. I couldn't recommend more just upping your CFD skills now. Even if it's just 2D and airfoil and you figuring out how to change the angle of attack of the inlet velocity coming in and understanding different airfoils and as flow separation occurs and things like that. I mean, you're going to market yourself so much more than I think I was prepared for when I graduated. So without further ado, this is outdated. I did this last year. What's that? Was there any preliminary questions? I know, Emma, you said something about that, or was that we're going to wait till afterwards?
We're actually going to wait until afterwards so that we can give everybody a chance to, if you have any questions that you want to ask about the presentation, we have a link in the Twitch stream chat so that you guys can actually ask questions as he's going. And then we're going to open it up at the end of this for more questions.
So I won't see those because I'm just going to be staring at my own presentation, and it's a rather long presentation. I'm going to go through it much faster than I've done in previous presentations. But if anybody does have something, because we're going to get into meshing, boundary conditions, all the things like that, and really the time for a question might be instantly. So please feel free to interrupt me if need be. Otherwise, I'm just going to keep babbling.
All right, I'll keep an eye on the chat for you, Sean.
So CFD is used in aviation. Here's a conglomerate of different studies that Boeing uses for CFD. And I'll post or I'll send Emma this to be distributed if anybody's interested. This might actually give you inspiration, as a master's thesis or something like that down the road, just to see what other companies are doing with this. Same with Airbus, but aviation, aerospace, it's really neat. We can kick it up a notch and study compressible flow. We can identify normal oblique shocks, maximum dynamic pressure on the vehicles as they ascent. We can identify overexpansion or underexpansion of nozzles depending on your boundary conditions. If you just wanted to design a simple rocket nozzle. And it's used everywhere else too: automotive, biomedical, HVAC, oil, gas, even sports. Actually, Speedo was the first LLC to use CFD. Like, I don't want to make up the year, but it was before like 1980. And they used it on their Speedo to minimize turbulence off of their material they were using and drag. So that's kind of interesting. Where I've used it, so we had a couple problems with our flight. So part of FAA, our aircraft has to get down to 45 knots stall speed. So that's flaps fully deflected. So the flaps deflect based on not just the airfoil selection, but the hinge that it rotates about. So this is a little example. If you put the hinge here, well, here's its corresponding flap, the brown versus the brown, or the green versus the green. And you can study, and wow, does it make a humongous difference of the performance. And let me see if I can, yeah, here we go. So I can do a design study, and I don't know if you guys can see my mouse, but we're looking at a lot of flow separation over the flap. And if we can get that flow to stick by making this flap overlap and gap in the right position and almost kind of create a nozzle that just high pressure moving air over and keeping it from separating, we're going to get a lot more lift before stall. So I can't even begin to tell you how many times I have repositioned this flap and figured out where exactly we should put it to get that maximum. So we ended up cutting our stall speed by 7 knots just from that one study. And again, that's huge because the FAA won't even consider us if we're not at least in the ballpark. Some of these videos don't work. So how are these complex fluid problems solved? Any Zoolander fans out there? Doesn't matter. So mathematical modeling, we've all had to see this at one point or another. Mass conservation, conservation of momentum, which is essentially Newton's second law, right? We have mass, the density of the fluid, times acceleration equals your force. So F equals ma. These are your external forces due to pressure. Sorry, your pressure forces. These are your external due to gravity, and your viscous forces. So basically, at every single cell, which I'll show you in a minute, we're going to discretize the aircraft and the fluid around it into little boxes. And just like so, just slice it up. And if any of you pursue your master's, this is the first thing you're going to do in heat transfer. And you actually have to make your own calculator through Python or MATLAB and say what's happening at this cell is moving over to this cell, which is happening up at this cell, and up and down and left and right. And you have to do that for an entire grid. But that's the basis of computational fluid dynamics or finite element method. That's actually what it is the finite element method. And at each one of these squares, it's solving conservation of mass, conservation of momentum. And later on, you'll add turbulent equations so you can actually predict when flow separates and what the effect of turbulence is. And it's amazing what happens at each one of these cells because you'll get up to 16 million easily, but then you need supercomputers. So the process starts with meshing, discretizing the problem. Here's a wing section that I did. And a fluid domain. You can do hemispherical, semispherical, or even bullet shaped. There's 3 types of mesh. These square are hexahedral. They compute, in my opinion, the fastest, but because it's structured, when flow starts to separate off of your aft end parts of your wing, because it's so structured and it's talking from cell to cell, it doesn't really replicate what is happening in nature. And the closer you get to a surface or a curvature, it'll refine the cells, as you see here. But because it's structured, they don't talk with each other. They don't talk with the transport equations about turbulence very efficiently. So then when you move into unstructured, tetrahedral, triangles, it's chaotic. There's no sense in the structure of it. That's why it's unstructured. So you can make it so as you get closer to a surface, refine the mesh, and you can also make it aft of your test subject to refine the mesh because that's your wake region, and you're really concerned about what's happening in the wake region, turbulence, things that cause drag and whatnot. And then there's polyhedral, which is what STAR CCM uses. It's like the latest form of meshing that it's the most efficient, it's the most chaotic, it captures the most natural phenomena that's happening. And then I'm sure you guys know about the boundary layer, and as you approach a wall, velocity becomes zero. Well, you have to capture that. In fact, that's the most important part about CFD with any application is how are you going to capture the flow phenomena at the wall? So you have to use Prism Cells, which basically, as you see between the free stream and your boundary layer thickness, you have a exponentially moving thinner layers. So we can easily see 3, 4, 5, 6 layers, but right in here is probably 25, 30 layers. And there actually is a method to that madness in determining that. Just going back to your aerodynamic theory that you're learning now, starting with the Reynolds number, finding your boundary layer thickness, determining your skin friction coefficient, then the wall shear stress, friction velocity, and there's step-by-step formulas for doing this. It's not meant to be confusing, but it is a breadcrumb trail nonetheless. But it eventually comes out to saying, hey, with your velocity and your chord length or characteristic length, you're going to need 45 layers to accurately capture your boundary layer. It's pretty cool. But incredibly important in aerospace applications. So then you go to, once you're ready with that, you're going to have to mesh refine and mesh refine. And this is what happens when you start off too conservative. It literally takes your, I mean, look at that winglet. That's disgusting. It's horrid. But and your leading edge. I mean, and the funny thing is actually the program will let you run this. And I mean, I couldn't imagine the drag numbers that would come out of this because that's the way it's interpreting the shape that you gave it, which is not that. So you can get more and more refined until now you're starting to see, okay, my wing tips and winglet tips and where I'm having really small radius of curvature is now refined enough, and that's where those black regions are. Now it's starting to look like the shape. This is going to converge, and that's the hardest part about any, or the most frustrating, I should say, is getting your solution to converge. I mean, it seems like you'll try everything and still it won't converge. That's why having the access to a full ANSYS version that you have right now is so important, because with the student version, you only get 500,000 cells. That sounds like a lot, but it's not a lot if you're doing a full aerodynamic structure. If you're doing a section of a wing, that's plenty. I did that for my senior designs, no problem. And a lot of times that's gonna get you where you need to go. But if you want to do full vehicle analysis, it's not going to work. And trying to stay under that 500,000 limit is going to get you back to looking like this for a full vehicle. So, in which it's just, there's really no point in even in doing it, because it's not going to yield the results that you're looking for. A lot of cool mesh quality tools to tell you how fast. I'm not going to get too much into this, but when you start diverging and your problems aren't solving, there's a lot of cool tools in STAR CCM at least. And I'm sure there is in ANSYS. I'm only using STAR CCM because that's what my company uses, but I started off with ANSYS. But there's a lot of ways to figure out why you're diverging, so you're not just pulling your hair out or give up. See, even when you think your mesh is very refined and you zoom all the way in on your wingtips, in this case, it's a winglet. It's a very thin surface. Look at all those jagged edges. That is going to be what the problem solves against. So if you want, and the problem becomes computational power at that point, which now we're using 256 cores on a cloud computer. You know, I couldn't dream in a million years to run this type of problem on my laptop, but I have in a much coarser grid, just like what you're seeing here. I had to accept that my geometry wasn't going to be perfect, just to try and play it out and learn. So here's some of your different fluid domains, and the options for boundary conditions. If you're just wanting to put air moving over a vehicle, you can do velocity inlet or free stream. Mass flow inlet's perfect for pipes, HVAC, where you're starting at the mouth of a duct or something like that. Stagnation inlet's awesome. Actually, it's really the only thing you can do if you're going to do a combustion chamber and rocket nozzle analysis. You actually make your combustion chamber the stagnation inlet. You set the temperature and the pressure, and then it releases, and you can see what happens after that. So learning the boundary conditions for what application is important. And then same with outlets. The pressure outlet actually works in every situation, but symmetry, you know, going back to my full aircraft, or even a pipe for that matter, why would I do the entire pipe when we can assume that on the other side, now, when there's a bend in the pipe or a sharp turn, we can't predict what's going to happen. Well, actually, I take that back, because you can cut the pipe from the top down and still capture the sharp turn and see what's happening on the lower end of the pipe. So any way you can to say, because it all comes down to computational budget, what you have and what the time you have too, because I have let simulations run for 72 hours and on, um, depending on what computational resources you have. So split it in half any way you can. And ANSYS or STAR CCM, you're going to see symmetry, boundary conditions. There's a lot of tons of tutorials online. I taught myself all this, and like I really wish UCF actually, at least in undergrad, drilled this down a little more. I know in masters they actually do offer courses for computational fluid dynamics and heat transfer, actually two of them. But I really feel like it would be useful for undergrads. But anyways, go ahead and skip that. And there's the physics models. Do we want viscous or inviscid, incompressible or compressible, turbulent, laminar, so on and so forth? You know, like for us, I can assume incompressibility, which makes my life a lot easier in a general aviation aircraft, because we're less than Mach 0.2. If anybody's taking notes, less than Mach 0.2. Oh gosh, I hope I'm not doing that wrong. Or is it 0.02? No, it's 0.2. Anything less than 0.2 can be deemed as incompressible. There's not a whole lot of density changes in the fluid happening that is going to yield the need for compressibility, which is going to make your solution times longer and whatnot. So general aviation, incompressible flow. The density is not fluctuating as the air passes over the body. Definitely turbulent though. when we're going at high angles of attack and we want to see where we stall. Yeah, I don't know if any of you guys have had to use X-foil or AVL, Athena Vortex Lattice, but they don't capture stall. It just keeps going. It'll tell you you're still climbing at 35 degrees, which is just not the case in reality. So uh, you want turbulence in your problems. But anyways, that's in ANSYS STAR CCM. You're going to set up your physics models, which actually I'll get into right now. You have K epsilon, you have Reynolds stress, you have K omega, Spallert, Alvarez, large eddy simulations, Reynolds average, large eddy simulations, all that. Some of them are better in terms of fidelity in how they capture turbulence than others, or some work better in internal flow like ducting versus external flow like what I do over aircraft. And there's guides out there, and even in I compiled a list of most of the main ones. This is what I use, the SA model, Spallert Alvarez, and it's perfect for, well, it's what's nice about it is it's one equation turbulence. It's super stable, it's good for external flow, and I converge every time with it. And I've done K epsilon and I've done K omega, and I've gotten it to converge in 3 or 4 times as much computational power and time in general. But when I send this out, you can kind of read some of the different advantages and disadvantages of these different turbulent models, because you will be faced with these when you open up a CFD application. And like me, the first couple times, I'm like, what does any of this mean? What, like, I couldn't wrap my brain around it. And really, the best way to learn anything is just to try it. And the best way to try anything in CFD is just to do two-dimensional, because your computer, your laptops that you're using now or whatever will rip through a 2D problem, no problem. So I've done benchmark testing of every single turbulent model, and towards the end in a Q&A, I'll see if I can pull it up, but you can see the actual, it's in this format, but over a two-dimensional cross-section of an airfoil. And you can tell for yourself which one has more fidelity, which one do you like more? And then when you go and realize that the Spallert Alvarez that takes a fraction of the time gives you the same, or if not close enough, results, you might want to stick with that one. So SA model, stick with that if you're doing external flow. And then your initial conditions. Basically, I'm just going to skip here. You're going to have your pressure. You're going to have your turbulent solution. These are all equations, your continuity equations, motion. And you're looking for, when you start a solution, you're going to get bombarded with a residuals plot. Now, the residuals basically mean that the answer now at this iteration minus the answer at the last iteration, this is the difference between the answer that was given. So if I'm looking for, let's say, my lift coefficient or my drag coefficient, when it first starts, like the difference between my last iteration and my current iteration is 1. And that's huge when you're talking about a lift coefficient. I mean, it's unacceptable. So the rule of thumb has always been 10 to the negative 6th, which you're saying you're going out 6 decimal places and saying, okay, I accept that the answer's not changing that much. Because when you go to report your result in your project or to your boss or something like that, how many decimal places are you going to go anyways? Like 2 or 3. So I'm personally satisfied after 10 to the negative 3rd, just because that's as far as I'm reporting. And unless it has some horrible oscillatory motion, which I'll show you what that looks like this. I mean, it just never it never converges. It just stays static. It's oscillating, and it never. I mean, it kind of gets lower, but this would be you'd want to stop this and figure out what's wrong after this many iterations. You wouldn't want to report this. You can't trust this information that's happening. So that's all residuals are. They're the difference between the current iteration and the last iteration. So as long as it keeps going closer to zero, that means your solution is becoming more accurate. I don't know why it took me a while to figure out what that was. Like that didn't stand out to me online. So hopefully that makes sense to you guys. Here's a process summary. We could go through it, formulate the problem, model the geometry. I will actually say this, one thing that I haven't stressed enough, because I work with people, mechanical engineers that are working on ducting systems. And in fact, let me actually, you know what? I'm going to show you some actual real life examples, but I want to go through the pre-processing segment of this real quick. And we're finishing up here. I think this is the most fun part, is when you can visualize what's going on. So if you check out this cow here, I thought this was funny. I'm also a total loser, but I saw this cow at Mach 8, and I got a lot of laughs around the office, but that's because we work in the field that we do. And then there's a T-Rex and a ram, if you will. I'm sure everybody's seen the meme of something and then lobster aerodynamics, something like that. It's good. It keeps us going. A lot of this content, I guess I deleted from my Google Drive. So, but so here's different types of post processing, so you can show your work to people. And this is really, unfortunately, nobody's going to understand what we do unless we can show them. So this actually is probably the most important part, and has been the most time consuming for me, at least, was getting the right color fields to accentuate the pressure fields or velocity streamlines that I want to display, that goes all the way up to my CEO, who's really only concerned about aerodynamics because he's an ex-Air Force pilot. And so this is how I sell my job and why we need this and got to keep doing this. So 3D contours, the contour is basically just the color differentiation, and which represents pressure field. And then, of course, streamlines, actually showing you the flow around. This was a static port analysis I did just to validate that there was atmospheric pressure in the center where the static port pressure was going to read, because avionics and instruments will not read correctly if you have your static port out here reading a positive pressure, or upstream where you have a lot of pressure fluctuation. So that's actually accomplished by putting a little lip and creating a turbulent drop off, if you will, and it ends up making a static ambient pressure field that makes the avionics read right. 3D streamlines, it's good for vorticity, seeing the effects of winglets as the I actually have something here. Well, I'll show you guys those examples in a second that are outside of this presentation. This one's my favorite, is ISO volumes. And then whatever your ISO volume is there's several options, but my go-to with external aerodynamics aerodynamics is kinetic energy, kinetic turbulent energy, and showing you, let me see the wake that is coming off and let me see the vortex shedding that's coming off of these surfaces. And this is super aggressive, right? This is at stall, planes falling out of the sky, but it looked cool, so I did it and took a picture of it. And you can even see these webs in here, and the reason that they exist is because that's the mesh. And realistically, I should have refined the mesh out here to get more fidelity. But it looks like spider webs, and it's really neat. This actually was part of the package that I sent to my superiors when they offered me a job in computational fluid dynamics. In fact, without post-processing, I would not be sitting here talking about this or had the experience that I'm grateful to have without post-processing, because again, this connects the dots between what you do and what your boss, what your boss does, or people that are going to sign your paycheck, I guess, or give you opportunity. So this is how we communicate our work. And of course, outside of pictures, 9 times out of 10, all I'm doing is working in thousands of lines of data and pulling out lift coefficient data. And this could be by wing, winglet, wing fairing, rudder, elevator, H-stab, V-stab, anything you can think of. I can parse out data and say, look at the lift contribution of this component of the aircraft, and look at the drag component of this, and so on and so forth. And that's another thing that people get excited about. They say, oh, look what before the winglet, we had, um, 60 extra pounds of drag on the wing near stall. And with the winglet, it's amazing the data that you can pull out of this. So drag coefficient, lift to drag ratio, and yeah, there's so many more data points that you can pull out of what I just showed there. But for an aircraft company, it really kind of starts and stops at how much drag are you producing and how much lift are you producing at what velocity. And you can actually extrapolate that or interpolate that information into a lot of other charts, like CL versus CD, and thrust required, power required, all sorts of performance parameters. But so that's the end of that original presentation that I gave. And I guess I'll just breeze through real quick here. I did a flap redesign. Without CFD, there's actually no way I could have done this, but ended up getting us 28% more lift. And again, this was back in August. I've actually got our stall speed down now to 46.5. So we're actually in, like, the FAA is cool with where we're at. And the stall angle is an extra 14 degrees because, with CAD, being able to CAD and then take your CAD over to CFD, you're the designer, you're the aerodynamicist. It's just, and then you just live in that world for a week. And then you come out with positive answers because it's all, and it starts off as like just trial and error. But after you do something so many times, it's like, wow, all this stuff that I learned in school, and I'm starting to see all these patterns with just even geometrical design that, you can start to predict what's going to happen before it happens. And CFD gives you that vision of what might, just because there's so many times where I said this is 100% going to make our lift better and or reduce our drag, and I was wrong. And after I thought about it, my initial instinct told me this, but after I thought about the reality of the situation, I was like, no, that actually makes more sense. And maybe that's just me because I don't think hard enough about stuff. But here's some more cool renders. Here was an inlet outlet. Right in this area here is a cooling system. So we have a radiator and a heat exchanger. And those two products that the mechanical engineers gave me said, we require 500 CFM of airflow going through this duct. Well, they had this duct going up and down and spaghetti, and like had no idea about static pressure buildup. and what that even means. So I tried to straighten it out. And actually even created a little Venturi here just for kicks because I was like on my 16th iteration of this design. And it ended up helping. This wasn't the final design we went with. We actually improved it more, but at this point, we got over 500 CFM, and before we started with CFD, we were at 212. So it's you can kind of see where that is in the aircraft. Same with this fairing. You wouldn't believe the contribution of lift and stall prevention that this, well, it makes sense though, right? Because when an aircraft stalls, it stalls at the root first. That's how they want aircraft to stall. It's a much more stable stall. So um, it makes sense that your stall can be prolonged a little more by just adjusting this geometry, this fat fairing here. But and anyways, I was saying this was from an old presentation too. I made all these composite parts, learned about carbon fiber, fiberglass, and stuff like that. We got to wear many hats in this company, but my passion is aerodynamics and CFD, and I think if you just know how to use and operate these things, and maybe even just do some of your own back end studies yourself, and kind of build a portfolio of just pictures and images that you can one day take to an interview and say, yeah, this is what I've done, and this is why I'm confident in doing it. I mean, it doesn't feel like work to me. I feel like genuinely anybody that signs up for aerospace engineering or mechanical engineering with a passion in aerospace, you know, when you can do just that, it's there's no like sometimes I'm like I can't believe these guys are giving me a paycheck. It's just fun, you know. I could do it all day, discovering more about and building my experience of how the phenomena of air flows over, you know, an engineered vehicle. So with that, I'll pretty much wrap it up there.
Awesome. Thank you so much for talking to us about that, Sean.
Yeah, no problem.
Yeah. All right. We do have a few questions as well. Let me take a moment and find them. So our first question comes from Jared, and he's asking what your favorite part of working at Bi Aerospace is.
Um, I don't want to be lame and say the community because I feel like that's such a standard answer. But I'm not gonna lie, when I graduated, to me, getting a job at Boeing, Lockheed, Blue Origin, NASA, SpaceX was everything to me. That's all that mattered. And I sent out a zillion applications. And um, I don't, I mean, I did internships, I did projects, I did everything. And I'm like, and my grades weren't bad. And you know, like for one reason or another, um, you know, I started applying to other things too. And um, when I got hired at Buy, a lot of my superiors who came from Boeing, who came from SpaceX, who came from NASA, who came from all those companies I just listed off, people that I'm working for. I mean, the being able to reach over with an arm and say, "Hey, Jim Forrester, who built turbine engines for GE, how, you know, for 25 years, how do you do this, that, and the other?" Like and I'm sure you get that access to knowledge anywhere. But all of them told me the same thing. Like, no joke, everybody said, wow, I really wish I would have gotten my first gig somewhere as small as this, because the hands-on information and the hands-on work you're going to obtain and experience will will set you up for a better position, I guess, if you decide to go to a bigger company. And I don't know what I don't know. So, you know, I don't feel like any of the opportunities I would have been given would have led, like I said, I actually got hired on here as a mechanical designer, and the reason it's such a small company was I basically made a case and said, stop spending hundreds of thousands of dollars on stuff that I can do. I went to school for this, and they, within a month, I thought this was going to be like a 2-year plan, like I'll just kind of bite the bullet, and put my time in. And they pulled me aside 2 months later and said, we want you here. And I was blown away. So it's small. Your opinion absolutely matters. Uh, these parts that I made here, they're on our aircraft. They're going to get manufactured, and there's going to be thousands of them. And it makes me feel like, wow, they actually trust me. It's like, oh my gosh, they're trusting me to make these and do the stress analysis and CFD over this. And when I give them a report, they say, all right, good work. Now let's make 1,000 of them. It's like I've just heard from my superiors or even coworkers who have come down from big companies to this company that say it's incredible how my voice is heard here. So that's really why I like. But again, this is my first job in the industry after I've graduated, so I don't know what I don't know. I'm sure anywhere else is fun too.
That's awesome. All right. So we also have a question from Matt who asks, as a CFD engineer, does your job function mainly focus on analysis of aerodynamic properties of a certain design, or are you also using CFD to aid in the design optimization process?
Yeah. So let me. So this was a slide I had to talk about today in our. Let's see. You guys are seeing the wrong screen. Hold on 1 second. Actually, we'll just keep it like this for now, if that's okay. Here's just like the more recent studies that I've done, and I hope I answer this question correctly. We had the need to extend the fuselage 4 inches and the cowling or the nose or nacelle, whichever you want to call it, up 2 inches. Well, that's going to move our center of gravity forward. So without even getting into that right this second, I needed to validate, though, that our aircraft was still going to perform the same. Like those decisions were way upstream. And they say, hey, let's just double check, do some CFD, make sure there's no detrimental effects to that. The flap cove and the flap redesign, that was purely driven by CFD. I mean, down to the airfoil selection and the way it was carved out of the wing was 100%. In fact, I made the surfacing in CAD of that got sent down to the composite engineers to actually make it into reality, which apparently I didn't give them an easy task. It was like I was living in fantasy world and like, hey, the plane will fly perfect if you do this, but like going back to manufacturing practices, it was tough to make, but they ended up figuring it out. Here's something that I think answers the second part of your question was the horizontal stabilizer and the elevator. I think you guys will, any of the aerospace engineers who specifically have taken flight mechanics at this point will appreciate this. They wanted to know, where should the center of gravity be? And I'm thinking, okay, you don't actually need to run CFD right away to figure that out. But what you do need to know is where your aerodynamic center is. Where is the force, the magnitude of the force? Actually, the definition of the aerodynamic center of a wing or any part of a body is where your pitching moment equals 0, regardless of what angle of attack you're on. Now, when we're not moving in air and we balance a popsicle stick on our hand, we find the center in its level. And when we move it left, that's the center of gravity. But with aircraft, regardless of where your center of gravity is, your aircraft is still going to pitch at a certain point where your pitching moment is 0. It moves away from your center of gravity. And that's, no matter what angle of attack you're at, that's the pivotal point where it rotates. And so, okay, I figured that out. It's this arrow, it's this down arrow for the tail. And they wanted me to tell them where the center of gravity should go, though. How far forward should it go from the aerodynamic center? And so, well, you have static stability requirements, then you have dynamic stability requirements. And you guys have taken flight mechanics, you'll know Dutch roll, phugoid, short period. But here's an example. When you perturb the aircraft in steady level flight, you pull it up, it's going to oscillate until it goes back to equilibrium. Well, I ended up figuring out all these values down here, these data points, are actually center of gravity locations in inches. And what I ended up finding out, though, was, okay, we need about a 5 to 10% static margin. And your static margin is literally just the distance that your center of gravity is forward of your aerodynamic center. And you do not want your center of gravity aft of your aerodynamic center. You will be dynamically unstable. Your pilot's going to be fatigued. He will likely crash the plane. It's incredibly important. In fact, this was the biggest project so far since I've been hired, because it made me lose sleep. I honestly was like, this is what's going to make students either able to fly it or not, and get fatigued. So without going too crazy into this, because dynamic stability is a whirlwind, I ended up figuring out that in all of that, our horizontal tail and our elevator were undersized. We actually didn't even have the pitch authority that we needed to climb past 6 degrees. Forget about all the work that I've done. Well, it's in a different presentation, like trying to get the stall speed lower at 12, 13 degrees. We actually we weren't even able to get past 6 degrees because you have a pitch up moment and, you have a pitch down moment exerted by your wing, a large one, but it's against your center of gravity. So it's not as huge as you would think compared to the H stab. They actually balance each other out perfectly. And that's how you figure out where to put your H stab. Again, all verified by CFD. It doesn't all have to be. You can do lifting line theory, panel codes, vortex lattice method. Before, I'm not saying, obviously they made planes before CFD. But what I found, though, was the horizontal stabilizer, like if we can't climb past 6 degrees, we're going to be the laughing stock of all FAA flight tests, and this is going to be a humongous cost to our program. And so, like, this was actually a week or a month ago, I caught this before our critical design review, and I ended up recommending that we increase the surface area of the elevator, basically extend it inboard 4 or 5 inches. But that wasn't enough to make the plane able to pitch and overcome the pitch down moment of the wing. We need more pitch up moment. So I ended up having to take the H stab and rotate it, its angle of incidence, -2 degrees. So that gave us the pitch authority that we needed. And, I guess to kind of like roll back to the original question was, CFD was the sole driver of this flap cove and flap redesign, and like how to pivot the axis, how to pivot the flap around its axis of rotation. This was another optimizing case. This was oh my gosh, like this has been designed, and like the chief engineer was fighting me on this, and I'm like, it's kind of cool when you are the one that possesses all of the data to be able to say, look, Tom, like, yeah, I mean, this guy has a world of experience more than I have, but I have the numbers in front of me, and I'm the one like in the weeds. And eventually to the point where he's like, okay, let's just go with what you're seeing. I agree. This is a problem. And it's kind of cool that CFD equips you with that type of thing to bring to your superiors.
All right. We also have a question from Eric who asks, with advancements in battery technology such as energy density, how did you guys design the structure and aerodynamics of the plane for implementing the future upgraded battery packs?
So depending on what side of the company you're sitting in, uh, you will think one thing or the other. Right now, we have all of our battery packs along the longitudinal axis, and uh, some of us disagree and think we should put the battery packs forward out into the wings, just like gasoline would. And there's a number of aerodynamic reasons why. If you think about roll acceleration and your lateral stability, um, imagine having all of your mass right on the center of axis of rotation, laterally speaking, right? Your rolls. I mean, think how nimble the plane's going to be without having any mass at all outside and having a larger moment of inertia. Basically, we don't have a large moment of inertia. What we have done, though, as far as it being current, well, we're also moving directly into the eFlyer 4, which is going to incorporate that. This has been a learning experience for all of us. Um, but I was in the office with our CEO, George Bai, and he said, Sean, feel this. He gave me a lithium ion battery pack that had, I think it was like 15 kilowatt hours storage capacity. And then he gave me another pack, and it also had 15 kilowatt hours, and it was lithium sulfur. And it's this company, Oxys. You can read about our partnership with them and what they're working on for this particular product. But it was less than a third of the weight of lithium ion. And right then and there, like it's one thing to read about that type of stuff, but when somebody says in your left hand is 15 kilowatt hours and in your right hand is 15 kilowatt hours, and one is just obviously way lighter, it's really interesting and exciting, and makes me even more excited to kind of be working on this stuff because it's going to be a plug and play um, swap is how we're designing this, with at least the battery cooling, the battery management system cooling, because that's what it comes down to, is how efficiently can you cool the batteries. That's why this one right here, this cooling system mass flow requirement, was such a big study. Was how much air can we pass through, how much heat can we remove from the coolant um, from these batteries. But with a battery that holds uh, the same amount of power, same amount of uh, amperage capacity, and weighs a third less, and is about a third smaller in volume, this plane will be ready to be souped up. Now, one thing that will probably have to be changed is the inverter. You might have if you're going to add more battery packs and they're all going in series, then you might have a higher operating voltage. So you might need to swap out your inverter, but you know, that doesn't mean that can't happen easily either. So I hope I answered that question.
All right. Let me find the next one. Uh, there we go. All right. When did you decide that CFD was what you were interested in pursuing a job in?
Ooh, I guess it's just being born in Florida, and I'm lucky to have caught a few space shuttle launches right before they ended. I think it starts with the inspiration that most of us have to even be in this club, right? And even be sitting here listening to me. And when I realized that the capabilities that CFD posed and I mean, there's only so much information you can read, but this is like CFD is truly putting your work to practice. Um, even down to the mesh, calculating the amount of prism layers you need to capture the boundary layer. Like if you were following through that process, it's like this is literally what Osbey was spitting at us, and probably at the time, none of us really. I'm not going to lie, like I'm not the type of student that caught all that stuff on right away, and it wasn't until I just what made me want to go into CFD originally was my um, my desire to move out of being a mechanical designer. I was craving I mean, I remember the first time I was asked to compute an equation because I moved away from GD&T, and I knew there was more out there for me. And when it was kind of like connecting the dots, you know, we're literally paying a third party company hundreds of thousands of dollars every time they do this stuff. And when they do it, there's a 2 week delay in getting the results. And then there's a design change delay. And then it's getting those design changes back to them. I mean, it was just such a lag in the program. So it was almost like without actually being creative and figuring out the $1 million next idea that we all want, the next $1 million idea for me was this company is lacking. Like here is the void right here. It's in front of my face, and all I have to do is learn how to click the buttons and apply the theory that I've learned. And I think that's kind of like a rare. If it's a small company, though, then the sky's the limit. But if you're going directly out of school for a CFD position, I would say absolutely. Like if this is what you want to do and you do want to work for a bigger company, please download the program. Even if you don't want to deal with the UCF software people, like just go download the free ANSYS version, and there is a copious amount of tutorials. It took me 8 weeks of just weekends, and my fiance now, like, she's like, "What are you doing? Like, you got to chill. Like, you've been working so much." And I was like, I was obsessed though. I was like, this is so much fun. Um, and like at the same time, I was like, I know if I can show this to my superiors, they're gonna know I should be doing more. It really came from a position of wanting more. I should say. I kind of got a job just sweeping the floors, if it for the most part, I would say, because I wasn't even doing a lot of GD&T. It was a lot of. Well, we won't get into that. It was yeah. So hey, could we take a 2 minute bathroom break or?
Yes, you are allowed. I will allow it, Sean.
Okay. All right. Sorry. I'll be back in 2 seconds.
Oh no, take your time, Sean. Alrighty.
A.m. this morning, and anyways.
All right. You're fine. Eric, whenever you're ready, we can unpause stream. Oh, okay. Never mind. That's fine. Okay. All right. So, welcome back, Sean.
Thank you.
Yeah. And I do want to say that our faculty advisor, Dr. Raghavan, is watching right now. And she said that passion for your field is so important and that this is a really inspiring thing.
She
So
was
I
my
just,
aerospace structures professor. I'm glad to have you.
oh, that's so good. All right. And then Jared asks, as someone that hasn't gotten an internship, would you say that projects weigh the same in terms of experience?
Absolutely. Now, um, I don't know if they're equal or not. I was working a lot on something outside of my field that was putting me through college. And I always beat myself up for that, that I didn't. So the least I could do in the meantime that I thought was as many projects as I possibly could. And at least for landing this job, I did put together a portfolio of everything I did, and one of which was the rocket design project for AIAA my first semester at UCF. And you know, those were the key. They really all they wanted to see. Uh, I can't say, because there's one thing that I'll say that I lacked was any type of industry knowledge. Design substantiation documents, SCD, source control drawings, just the mumbo jumbo that floats around in the industry that I had to catch up on quick. But they were able to see through my portfolio and my creative process, or at least what I was able to contribute in the projects that I was with. I mean, they said explicitly, this is why we're hiring you, was because of those projects. So for me, the next meeting that you have with somebody that only had internship experience and didn't do projects, I'm sure they landed their job that way too. So I would say if you're in a particular position like I was, where um, you weren't sure if you should quit your job because it's going to cut off your cash flow, that's make allowing you to pay rent out of the city that you grew up in just so you can go to school. There's always ways, but I would definitely not. Um, I would definitely not do nothing. Absolutely be involved as much as you can, and anybody who's sitting here right now is already doing that. So um, don't beat yourself up for it. Somebody will recognize the work that you're doing now, and a lot of times these projects, especially if you want to be a design engineer. Um, I have several friends who were in internships, and I was so jealous of them at the time for the names that they were able to put on their resumes. And a lot of them would say, don't be jealous, man. I'm compiling PDFs and filling out orders for, and I'm not saying that that experience isn't good either, but if you can get involved creatively in projects and be a rock solid member of your team, contributing to the design of something, anything that makes you overcome a problem, I see a lot of value in that, and it's proven to be value for me at least.
That's awesome. All right. This is a question from me, actually. What is some advice that you wish you received before graduating and going into industry?
I'll be biased just because I'm an aerospace right? Like I breathe this stuff, and it's honestly this CFD endeavor that I've gone into. I'm in the process right now of I'm saying, hey guys, we're an aircraft design company. Why don't we have an aerodynamics department? And just trying to like plant the seed there. Um, but I guess like I came out of school with all of this knowledge, and it wasn't until I was in this position did I actually bring it out and start using it. And I was just so ecstatic. Um, Whipping out, like, I mean, I can't tell you enough times I've taken out, at least for flight performance, hand calcs, like bringing out Dr. Zoo's lecture notes and stuff, and textbooks that I had. And um, I'm sure most students won't see it the way that I did. I don't want to say I was just trying to like stay afloat and get through school, because I really was interested in everything I was learning, but I don't know if it was the amount of workload I was putting on myself and kind of creating the inability to genuinely absorb the information that was being given. But really do pay attention to this isn't like something that you disagreed with maybe even 10 years ago in algebra or something, or where you're like, I don't want to say like, when am I going to use this type of thing? Because obviously we're learning all this stuff for a reason. And I guess I just couldn't have been more blown away by how much I use every single thing I've learned in college in my job. I mean, it I'm going back to freshman year notes, solid mechanics, aerospace structures, like, working in composite design. We're constantly throwing. I've had to develop tensile and shear stress calculators for in Excel for um, you know flap hinges that were connecting to wing ribs and things like that. And I had to size the composite, and I know the allowable stress of one piece of carbon fiber. And because of that, I know the stress and the moment exerting on the flap when it's fully deflected. And I'll say, okay, it's this much stress. This is the allowable stress. And therefore I need 11 plies here. And it's just, again, I like, some people might be like, no, duh, you're going to use all this stuff in industry. But like, I truly didn't see it coming. I mean, like, really keep a nice organization of all of your materials, because what you're learning now is what you're going to do for the rest of your life if you choose to. Um, and my other like strong, the bias coming from me is, if you really are interested in aerodynamics, take advantage of this time now and learn CFD. Because if you think it's as cool as I do, like understanding the phenomena of how these incredible machines, get into orbit, or just efficiently cruise at 5,000 feet, um, you can be the answer and the sole reason why a program actually gets to its goal, just because you were there to do the CFD on it, and either say, hey, when you're in industry, it's not like I think it's going to be this, and a lot of it is, you have to make a decision like right then and there. You can't juggle it forever. The program has to move on. Otherwise, we wouldn't have two astronauts that just launched last week. There are people just like us in the with our education who have to come to they have to come to a decision, and CFD does that. It can definitively say yes or no, and you can sleep at night because of it. And it's fun work. It's just absolutely rewarding work to see your designs progress based on your aerodynamic theory you're applying to a computer software, with saving companies hundreds of millions of dollars. Because if you wanted to do this in a wind tunnel, you'd sneeze and cost them $250 million just to make a model and then rent the space out, not to mention the data accumulation and things like that. So just do CFD, and also just, I mean, it sounds so cliche, but just, oh my gosh, pay close attention to everything you're learning, because whether you remembered it or not, which I know at times it's hard to juggle everything, it'll be pulled out again at some point, and you're at least going to be happy that you were familiar with the concept, but you'll be going back to your textbooks or even to your lecture notes, and applying them.
right. And then we're going to have one last question. This one is from Matt again. And he's asking if you could elaborate on what your portfolio topic is, and if if you compiled the portfolio in addition to your resume, and how you would submit that with a job application.
Yeah, so most of the time, the application will have a separate place to upload your portfolio. In my case, I just did it through Indeed with my Indeed resume. So I had to retype everything or copy and paste over vital information. And I got the interview, and it was the second interview that they said, the on-site interview that they said, if you have a portfolio, bring it with. So I went to FedEx and got a nice buttoned up copy of it. And actually, I made it the night before because I didn't have one and I didn't want to show up empty handed. And the scope of it was, let me see if I can, are we still sharing? Well, I don't need to show you. It's just, well, you know what, maybe it'll help. I'll just skim quick.
We are still sharing, so.
Let's see.
Stopping the share just for a second to not show any info.
You know, pictures for sure. I mean, I did so many projects that it exceeded 14 pages, and I had to leave out one or two projects, which I just had to figure out what the weakest link was. But I probably had in all was 4 or 5 projects, one being my senior design. And you know, it's going to be super easy to write if you today say, hey, the next project that I'm going to do, I'm going to take a leadership role in it. And or at least I'm not going to do it just because I want to put it on my resume it's easy to put 2 lines, but if you want to talk about something in your portfolio, because that was the part that it wasn't my resume when they said, okay, you're hired. It was the portfolio that we were going through. You know, I probably had too much writing in it, honestly, because they're not going to read it right then and there. But however, if the job application asks for a portfolio, then you don't know. Maybe they will read it all. But if you're going to be asked to go through it in your interview, then you're not going to be able to speak to 1,000 words as quickly as are a few snapshots of very vital milestones in your project that happened. I don't know if I answered that as helpful as I could have. I just think it's good to start at least compiling. At some point when you graduate, you're going to see how many times people have asked you for or a place to put your portfolio. And of course, you don't have to do it. But I also, of course, didn't get even a call for an interview, you know, as many times as I applied to places. So you always got to think, well, what were my weak links of my application? Was it because I didn't have a portfolio? Was it because I didn't have a cover letter? Or I would say for sure, at least always a cover letter. I think that's what landed me my original interview, was because it puts some personality and some passion into, you know, what your goals are and how you think you might best be fit for them. I guess like my ultimate answer there for resume, cover letter, or portfolio is just put your heart into it. There's guidelines online to, you know, I guess there's certain things that you shouldn't do. You don't need to you don't need to elaborate a ton on every key point, but I guess that's kind of like the progression, right? Your resume is just this blank robotic version of you. Your cover letter is like the first time you meet somebody and the first conversation you have. And then your portfolio is like, hey, I've known this guy. We've hung out like 10 times now and I know who he is, type of thing. And And if somebody's interested in you, like from the first one or two items, and they make it to the third, you got the complete package. And I don't know, just, yeah, I don't know if I have a perfect answer for that.
Right. And that's fine. Honestly, I feel like the advice that you have given today has been really beneficial, and especially for someone that is in the position of the viewers. I really do appreciate all that you came to say to us today. And
Sure. Thanks for having me.
yeah, of course. And just thank you so much, Sean, and thank you to all of our viewers today. We really appreciate you guys coming out here, and we hope to do more events like this in the future.
Is my screen still sharing?
Yes.
If anybody has any questions, just shoot me an email anytime. I'm a UCF student still, and it is a lot of fun getting to talk.